Hey everyone, welcome back, and today let's solve Leetcode problem 2211 titled Count Collisions on a Road. So very quick kind of summary of the problem statement here. Effectively, we're given a string directions of the string L, or rather character L, character R, or character S, and each character would be a car, where L would move left, R would move right, and S would simply mean stationary, in other words, not moving. Now, we know that the cars move simultaneously, so when two cars meet, or a moving car hits a stationary car, they would collide and both become stationary. And our task is to return the total number of collisions that would happen until no car is moving, right? So, to kind of just gloss over the examples really quickly here, notice how the direction is essentially a string with three different characters at most, which would be R, L, or S. And effectively, the car at this position R is effectively going right. The car at this position L is effectively going left. So you can imagine that these two cars would indeed collide with each other and become stationary. The same would apply with this left car and the stationary car, or this right car and the stationary car. And this left car would eventually also hit S, except it's 2 units away instead of just being 1 unit. And kind of summing up all the different kind of time, or rather number of collisions that would happen on the road until all the cars essentially stop moving, that would be 5. Why is it 5? Well, we know that cars 0 and 1, meaning this car would go right, this car would go left, they would collide together. And since they're moving in opposite directions, one's going right, one's going left, we know that they'd collide together. And so they'd then stop and become stationary, right? That's going to be, one collision. Right? We also know that cars 2 and 3 would also collide with each other. And since car 3 is stationary, the number of collisions would become 2 plus 1, right? It'd be this guy hitting that guy, the other guy hitting this guy, and right and left colliding with each other. So that's a total of 3. And kind of applying that same logic to all the other potential collisions with all the other different cars, we see that there's a total number of 5 collisions until all the cars would stop moving. Again, a car stops moving if it collides with another car, right? For example 2 here, there's actually going to be 0 collisions until all the cars stop moving or become stationary. And the reason why is because these two cars are going left, meaning they're going in one direction, in other words, the opposite direction, and these two cars are going right, meaning these guys are going in this direction. And so they're actually never going to collide because there's never going to be a point of time where they hit each other because both the set of cars or both pairs of cars are going in opposite directions, right? And so there's going to be an answer of 0. So for the constraints here, we see that the length of our directions input array is going to be between 1 and 10 to the 5th arrays. In other words, basically just the number of cars that we have. And we're also guaranteed, kind of just confirming what the problem statement said, that directions at any index I is always going to be left, right, or stationary. Which brings us to the main kind of our high-level solution and trick that we really need to make to be able to solve this problem efficiently. And the thing is, really, cars at the very left that are L, they're never going to collide with anyone because they're always going to move off the road leftwards. A good example of this is example 2, right? These two cars here, since they're at the very left edge of the board and they're moving leftward, they're never ever going to collide with anyone because they're already going off the road to the very left, right? And so they're never going to make any collisions. They're never going to actually become stationary, right? And so what does that kind of mean in terms of an observation that we can make? Well, no, we know that leading L's are always going to be safe. They're never going to cause collisions. And applying the very same logic to this pair of cars at the very right that are moving right, or in other words that are also never going to collide with anything because they're always going to move off to the right of the road, right? And that's going to tie into the other observation. Trailing R's are also safe as well. And so basically everything between the first non-L from the left and the last non-R from the right is going to be the region where collisions would occur or be resolved into stationary cars, or S's. And one more very important observation apart from those kind of main kind of tricks, if you will, in that middle region that I just talked about, every L or R will eventually be involved in at least one collision, and that would then contribute to +1 to the collision count. And S is already stationary, and since that itself doesn't cause a collision count, because although it can cause others to hit, those are already stationary, right? The ones that actually cause us to hit are going to be left and right. And so basically, if we trim off the safe leading L's and the trailing R's, the answer to this problem is quite straightforward. It's really just counting how many characters in that remaining middle substring are either left or right, and basically not S, because we know that stationary cars are already stationary. We can't count them again or overcount them for collisions because they're already S's. And so how are we going to really solve this problem in an overall structural array? Well, we're going to compute n, right? And again, usually n is simply just the length of our input, just kind of for reference. And then once we actually get the length, we're going to move L forward while directions at L is going to be left, basically just skipping the leading safe cars like we talked about a few minutes ago. We're going to move R backward while directions at R is equal to R, basically just skipping this trailing safe cars. Really just the same thing that we talked about just now. And if L is greater than R, that means there's no middle region, and then we'd return 0. That's what example 2 really was. L would be greater than R. And for all the indices I from left to right inclusive, essentially again that middle region where there are cars that are guaranteed to cause collisions, we'd add 1 to our collisions count for each directions at I that is an L or an R, but not an S. Right? Basically, in other words, if directions at that index I is not equal to an S. And finally, we'd simply return the collisions, and that would give us a linear runtime in a constant space. And so kind of just summarizing what exactly this whole solution was. Right? Now, this problem really isn't too complicated if you really think about it. It's just these little observations that really add up to make our code a lot simpler than it really needs to be. Now let's go ahead and get into the actual solution. And like I just talked about, I always get the length of my input and store it in a variable n. Now if it's a matrix, I'll use variables like n and m. In this case, there's really just one, it's really just a 1D data structure or an array, and so I'm just going to store the length of my directions or the number of cars that I have in this variable n. Once I do that, I'm then going to initialize my left pointer, right? And this is going to, of course, start at 0 because it's starting at the very left. And the whole point of this left pointer is it really just points to the first character or the leftmost car, right? And we're essentially just going to move L rightwards to skip all the leading L's that we know would never collide with any cars at all. And the very same thing for R, except instead of starting at the leftmost indice, it's going to start at the rightmost indice or the last index or car in our directions array, which is the length of our directions minus 1, because that is the last index. It's going to be the index of the last character or the rightmost car, and then we're going to move right or R leftwards to skip all the trailing R's that would never collide, right? So once we do that, now we can actually get into our main loop of skipping all the leading L's and skipping all the leading R's. Now first we'll do the loop for the skipping all the leading L's. So while L is actually in bounds, meaning it's less than the length of our input array, and directions at L is actually directions at L is actually a L character, if you will, meaning it's a left car that's going leftward, we're automatically always going to increment L by 1 while this is the case, because this is the part where we actually skip all the leftmost left cars, because we know that they're guaranteed to be a safe car, meaning they're not going to actually collide. Of course, we use L less than n to avoid any indexing beyond bounds and any edge cases like an empty string, or if we have all the characters be in L. Right? And inside this while loop, we're essentially just incrementing L by 1, because each increment would move the left pointer 1 position to the right, effectively just skipping a leading L car, and we'd repeat this again until we either hit a non-L character or we run out of characters in the string, meaning we hit the end of the string. Now, we're going to do the exact same thing, but in this case for the right pointer. So, while R is greater than or equal to 0, meaning it's still in bounds because we're moving R leftward instead of rightward, and directions at R, instead of being equal to L, while it's actually equal to R, what are we going to do? Or we're going to decrement R by 1, right? So R minus equals 1, right? So effectively, we're checking again two things. We're checking if R is still a valid index, and directions at this index R is actually a right car. Basically, just checking if it's the current rightmost car. And while both of these conditions hold true, our loop body would execute, very similar to the left pointer logic, right? Each decrement would move the right pointer 1 position to the left, skipping a trailing R, and we'd repeat this until we either hit a non-R character, or again, we simply run out of characters in the string, meaning we hit the very beginning of the string, right? Very, very simple, similar logic as the left pointer one. Now, once we do that, that's basically just getting our left and right pointers initialized or initiated to create our middle kind of substring that actually are guaranteed to have collisions. So now let's actually create that collisions count. So I'm going to call it literally just collisions integer variable, and I'm going to set it initially to be 0, of course. Now we're going to build this collisions as we actually check for all the non-S characters in our middle region that are guaranteed to have collisions, right? Basically all the non-safe cars. Now, let's first actually check if there even is any middle region, because like we saw in example 2, there wasn't even a middle region. How do we know if there's a middle region? Well, if our L is within bounds compared to R. So if L is greater than R, meaning our left pointer is greater than our right pointer, that moves our left pointer has moved past the right pointer. That means that after removing the safe leading L's and the trailing R's, there aren't actually characters left in the middle region, and so there would be no collisions possible in our input array nums, or rather our input string directions, sorry. And that would handle all the cases like any L's or all R's on either side of the string, like we saw in example 2, or also for the case of an empty string and things like that. So if this is the case, we automatically return 0. We're guaranteed that there's no collisions because all the cars would be safe cars, if you will, right? That were guaranteed no collisions. Now, this is where we actually begin iterating the middle region if left is not greater than R. So for I in the range of this middle region, which again is basically just between the 2 pointers inclusive, so from L to R, but remember in Python, the second parameter in for loops is actually exclusive by default, and so we'd actually have to go up until R plus 1 to include R itself in our loop range, right? Basically, our middle region here, we're iterating from I to L, X inclusive rather, and index I is simply just going to point to each car in the potentially colliding area. And we're effectively just going to inspect each car and decide whether it actually contributes to collisions based on if it has actually a left or a right, or if it's an S. Again, if it's an S, it will not collide. If it's an R or L, it will. And why it won't collide because it's an S? Because it's already stationary, based on what we said before. So, if directions at I in this range, in this middle region here, is not equal to the string S, only then can we actually increment our collisions by 1. Only then will it actually make a collision and contribute to another collision. Why is that? Well, because if it is an L or an R, then that specific car at this index I would actually eventually participate in a collision because of what we said before, right? S is already stationary and it doesn't itself increase the collision counter. That's very important. We don't want to overcount the number of collisions we have with extra S's that don't actually add to our collisions. Now, effectively, once we did that, we simply just return our collisions count to be the number of cars, or basically just the number of cars that have that are going either left or right in this middle region between L and R inclusive, once we eliminate L and R to be any safe cars, right? That would basically just be after processing the entire middle region, we simply return this integer collisions, which would hold the total number of collisions that would occur until all the cars collide with another car and become stationary in that middle region. Right, so unless I made any syntax 0, 0, this should be accepted and this should be a valid solution. So let's go ahead and verify that. And as you can see, this really is just about as efficient as you can get it to be. So I know I sound like a broken record right now, but just to kind of one last time summarize what we've done in this code. Effectively, we simply just counted how many cars are guaranteed to collide by ignoring all the cars that will never collide from leading L's and trailing R's, and then we'd actually find the bounds of the kind of active middle region, if you will, that actually do have guaranteed collisions, which would basically just be the first non-leading L to the last non-trailing R, and then we then simply just count how many moving cars that are going either left or right lie inside that region. And we know that each such car would contribute to the total number of collisions by 1, and we simply just return that count in the form of the integer variable collisions. Now, another kind of final observation to really make, each moving car inside that trimmed region must also change its state. It must either collide into some car or be part of, a multi-car collision chain. And so it will actually contribute to exactly one, or rather, it will contribute exactly 1 to the final collision tally. And that's why we computed it like that. The moment we found something that isn't an S in that middle region, we simply just added the collision by 1 because it's guaranteed to only add the collision by exactly 1, right? So for the runtime complexity of this solution, like I kind of glossed about above in the problem kind of explanation, or the solution explanation rather, the runtime complexity is actually linear. It is actually big O of n, where n is simply the length of our input string directions. Why? Because each pointer L and R would move at most n steps combined, and we know that the final loop would iterate over at most n indices. There aren't any nested loops, and so because of that, the total work would scale linearly with the size of our input, making it a big O of n, or linear runtime complexity. And for our memory or space complexity, it's actually constant or big O of 1 extra space, and the reason why is because we're only actually using a couple integers like collisions, n, l, and r. We're not actually using any auxiliary memory or any extra data structures. We're not actually allocating additional data, proportional to n, and because of that reason, it's actually going to be big O of 1, or a constant time memory or space complexities. Again, keep in mind, integers do not take up extra space with respect to our input. Only actual data structures do, like lists or hash maps or hash sets and so on and so forth. Right, and that's going to be it for today's video. If you guys enjoyed this video and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.